Chapter 16 deals with oscillatory motion and waves. There's going to be some equations on here and some figures you've seen before. And to be honest, you've dealt with oscillatory motion a lot in your lives. And this is just kind of putting equations to stuff that you already know, most like every other chapters we've gone through. So we're going to go through about 28 slides, and that'll cover most of chapter 16, which is all you need for this course. So for figure 16.2, we have the displacement from the equilibrium position. So we have when displaced from its vertical equilibrium position, this plastic ruler oscillates back and forth because of a restoring force opposing displacement. When the ruler is on the left, there is a force on the right, and vice versa. So whenever the ruler is on the right, there's a force trying to pull it back to its equilibrium position. And we know that the ruler's not going to just come right back to it. It's going to oscillate. It's going to go back and forth a little bit, less and less and less, until it's right there at that equilibrium position. So for A, you have the ruler was being released. The restoring force is returning the ruler to its equilibrium position. For B, the net force is 0 at the equilibrium position, so right there in the middle. But the ruler has the momentum and continues to move right. For C, it's the same thing as A, but the restoring force brings it to a stop here, and then the force goes in the different direction. For D, it is much like B. You have a velocity going in the opposite direction with the force here at the equilibrium being 0. And for E, you pretty much have the beginning of A, but here, in the absence of damping caused by the friction forces, the ruler reaches its original position. From there, the motion will repeat itself. So this motion repeats and repeats and repeats until the ruler stops right there in the middle at its equilibrium position. So oscillations of a spring, we've dealt with springs in the earlier chapters, and you'll see one or two equations that are similar to the ones that we dealt with before. So here, we have an object vibrates or oscillates back and forth over the same path, each cycle taking the same amount of time. The motion is called periodic. The mass in the spring system is a useful method for a periodic system. So here, you can push the mass back this way. Well, here's the starting position. They pull the force or pull the spring out. So here, this would be similar to here. This spring wants to restore itself back to where its original position was. So the force is going to push it back towards the original position, just like here, the force is trying to push it to its original position for the ruler. And then it's going to kind of overshoot it, right? So then the spring is going to be compressed here, much like it was right here for the ruler. And then it's going to bounce back until that spring reaches that first position, the equilibrium position. So we assume that the surface is frictionless. There is a point where the spring is neither stretched or compressed, so that's the equilibrium position. We measure the distance from that point, so x equals 0. That's the equilibrium position. The force exerted by the spring depends on the displacement. So here we have F equals negative kx, which is similar to an equation you've seen before, where k is the spring constant and x is your displacement. Multiply these two together with this negative here, you get the force. So it's very dependent on the displacement because your constant is going to stay the same unless told otherwise. So it's really dependent on this x. The minus sign of this force indicates that it is a restoring force. It is directed to restore the mass to its equilibrium position. K is the spring constant, and the force is not constant, so the acceleration can't be constant either. So that means your velocity is never going to be 0. So going back to that figure before, displacement is measured from the equilibrium position point. Amplitude is the maximum displacement. So if I don't think it shows a restoring. Well, let's say here, this spring here is compressed, and then it shoots out, right, trying to bring itself to its equilibrium position. Then it's going to oscillate back towards the other way with the force pushing it back towards the original position. It's going to overshoot it a little bit, and then it's going to go right back to that initial position. So essentially here, this is your equilibrium position. So the amplitude would be the distance of how far out this spring with the mass goes out. So a cycle is a full to and from motion. So from here to here, this is one cycle. Period T is the time required to complete one cycle. So the time between the spring is let go and starting at compressed, reached its highest amplitude, the maximum displacement, and then returned to its compressed state. That would be one cycle. And so the frequency F is the number of cycles completed per 1 second. The SI units of frequency is 1 hertz, so 1 cycles per second. So here we have frequency equals 1 over T, 1 period. And here is our 1 hertz, 1 over S. So here you can see that the units here are directly proportional to the equation we got. So another figure, 16.9, we have an object attached to a spring sliding on a frictionless surface is an uncomplicated simple harmonic motion, simple harmonic oscillator. When displaced from equilibrium, the object performs simple harmonic motion that in amplitude x and a period t. The object's maximum speed occurs as it passes through equilibrium. The stiffer the spring is, the smaller the period t. The greater the mass of the object is, the greater the period t. Okay, so it's the same motion as the other figures we've seen. If it's compressed, it's going to try to shoot the other way. If it's stretched out like it is, it's going to try to pull it back. You can see that the direction here, you can kind of see the mass coming back to its equilibrium position. So simple harmonic oscillator. For the period of a simple harmonic oscillator, we have T equals 2 pi square root of mass over your constant. And because 1 over T is your frequency, we can also dictate what frequency is based off of this. So frequency in this case for a simple harmonic oscillator, we would have 1 over 2 pi square root of k over m. So what is so significant about simple harmonic motion? One special thing is that the period t and the frequency f of a simple harmonic oscillator are independent of amplitude, of its displacement. The spring of a guitar, for example, will oscillate at the same frequency whether plucked gently or hard. Because the period is constant, a simple harmonic oscillator can be used as a clock. Two important factors do affect the period of a simple harmonic oscillator. The period is related to how stiff the system is. A very stiff object has a large force constant K, which causes the system to have a smaller period. For example, you can adjust the diving board stiffness. The stiffer it is, the faster it vibrates, and the shorter the period is. The period also depends on the mass of the oscillating system. The more massive the system is, the longer the period. For example, a heavy person on a diving board bounces up and down more slowly than a light one. In fact, the mass m and the force constant k are the only factors that affect the period and frequency of a simple harmonic motion. So it's really just these two factors here, because 2 pi is going to be, a constant. So it's these two factors that it really depends on. So example 16.4, we'll go ahead and find that in the book. If the shock absorbers in a car go bad, then the car will oscillate at the least provocation, such as when going over bumps in the road and after stopping. Calculate the frequency and period of these oscillations for such a car if the car's mass, including its load, is 900 kilograms and the force K of the suspension system is 6.53 times 10 to the 4th newtons per meter. So we know we have to use these two new equations we just found. So to find the frequency, we have 1 over 2 pi K over m square root, and we just plug in. So that 6.53 times 10 to the 4th over 900 will give us 72.6 over the units here would be 1 over seconds squared. square root of all that, and times the constant 1 over 2 pi. That'll give us roughly 1.36 hertz. Remember, it's frequency, so it has to be in hertz. And same thing for your period. You have m over k here, so you just plug in as well. And we also know that your period is 1 over frequency, so you already have your frequency. It's easier just to do that. So we get 0.738 seconds. That would be the frequency and the period of the oscillations for this car. So for this figure, we have the vertical position of an object bouncing on a spring is recorded on a strip of moving paper, leaving the sine wave. So here, some of y'all have seen waves before. This will be developed as a sine wave. And this is just this mass coming up and down on this paper. For this figure here, we have a simple pendulum. We did do a lab about this earlier in the semester. Has a small diameter bob and a string that has a very small mass, but is strong enough to not stretch appreciably. The linear displacement of equilibrium is S. So this S here, this is the linear displacement. The length of the arc. Also shown are the forces on the bob, which result in a net force of negative mg sine toward the equilibrium position. So because we know that this here, we have your tension up here, you have mg going straight here downwards, and you also have this theta. Well, we know we can break those up here into your x and y components. So here your S, or your negative mg sine theta, would be its restoring force technically, because this is going in the same direction as what this equilibrium position would be. Remember, if it oscillates like this, there's got to be that one point where it just kind of stops. Now, if we can show that the restoring force is directly proportional to the displacement, then we have a simple harmonic oscillator. Okay, so for a simple pendulum, in trying to determine if we have a simple harmonic oscillator, we should note that for small angles less than 15 degrees, your sine theta is roughly just going to be theta. They differ about 1% or less than the smaller angles. Thus, for angles less than about 15 degrees, the restoring force is proportional to negative mg theta. The displacement S, the arc length, is directly proportional to theta. When theta is expressed in radians, the arc length in a circle is related to its radius, L in this instance. We've used R before, but in these equations, we're going to use L. So we have our theta is going to be our S, which is our arc length, over L. Okay. So, but for small angles, we're going to use that our force is mg still, and then we're going to plug in this theta, the S over L. So that's where that comes in. But this looks very familiar to the negative kx, okay? Where the force constant is given by k is equal to mass times gravity over L. So this would be your k. And the displacement is given by x equals s. So these are going to be constants, right? And this is just going to be like your displacement. That's why it's similar to Hooke's law. For angles less than about 15 degrees, the restoring force is directly proportional to the displacement, and the simple pendulum is a simple harmonic oscillator. Using this equation, we can find the period of a pendulum for amplitudes less than 15 degrees. So for a simple pendulum, we'll have t equals 2 pi square root of m over k, which is the period equation we were given. But now if we plug in what k is, what we were just given over here for negative mgl, so we just take the mgl here. So now m's and m's cancel, right? And this g over L is at the bottom, so we can flip the L to the top. So our period for our simple pendulum is 2 pi square root of L over G. This result is interesting because of its simplicity. The only things that affect the period of a simple pendulum are its arc length and the acceleration due to gravity. The period is completely independent of other factors such as mass. As with simple harmonic oscillators, the period t for a pendulum is nearly independent of amplitude, especially if theta is less than 15 degrees. Even simple pendulum clocks can be finely adjusted and accurate. Note that the dependence of t on g, if the length of a pendulum is precisely known, it can actually be used to measure the acceleration due to gravity. So, for example, 16.5. What is the acceleration due to gravity in a region where a simple pendulum having a length of 75 centimeters has a period of 1.7357 seconds? So here we're asked to find g given the period t and the length of a pendulum, right? We can solve t equals 2 pi square root of L over g for g, assuming only that the angle is less than 15 degrees. Remember, if we're able to use this equation, we have to say that this angle is going to be less than 15 degrees. Okay? So we have to turn this equation to equal out g. So first, you would divide by 2 pi, bring that over here, square both sides, and then move the g to the right or to the left, and then divide everything else to the left side. So once you do all that, you end up with this, where you have 4 pi squared L over t squared. And now we have what we need. We have 4 pi squared, which is just um, a constant. You have 0.75 meters, because we turned the 75 centimeters into meters. And we have our period. So 1.7357 seconds squared. So that gives us roughly 9.828 meters per second squared. So that's fairly close to what gravity is. So for here, the transformation of energy is a simple harmonic motion is illustrated for an object attached to a spring on a frictionless surface. The total mechanical energy, for potential plus your kinetic, is conserved if there is no friction, and so that the total mechanic energy is given by Ke plus Pe elastic, and this is 1/2 mv squared plus 1/2 kx squared, and this in turn turns into 1/2 m L squared omega squared plus 1/2 mgl theta squared. But remember, it's constant, so it's conserved, so it's all a constant. But here we're saying that our V is equal to LW for rotational motion, and that K is mgl. So this is your K. This is how you get your mgl, and you have your V here, so you have L squared omega squared right there as well. So this means that we can solve for the maximum velocity, which happens when the potential energy is 0, so that the block crosses over x equals 0 point. Remember the equilibrium position. We find that the maximum velocity of a block on a spring is velocity max is equal to square root k over m x, which is x is the maximum displacement. Remember, this would be like your amplitude. Similarly, for a pendulum, we have omega max is equal to square root g over L theta max, where your theta max is the maximum angular displacement. So these are just equations we've seen before. This is just putting it in terms of what we just learned here. A point P for this figure, so right here, moving on a circular path with a constant angular velocity omega, is undergoing uniform circular motion. Its projection on the x-axis undergoes simple harmonic motion. Also shown is the velocity of this point around the circle, your velocity max, and its projection, which is your velocity. Note that these velocities form a single or similar triangle to find displacement to the displacement triangle. So here we have our velocities here, velocity max going this way, and obviously we can find our component velocity here. We have our x here. Big X here would be technically the largest displacement, so our amplitude, and we can find these 2 points. We have our omega going in a circular motion, and this point here undergoes simple harmonic motion. So here, this is just going like this. This is the equilibrium position. So for uniform circular motion and SHM, you have a point moving in a circular path with a constant angular velocity, omega, and is undergoing uniform circular motion, UCM. Underneath, you can see that the displacement in the x direction over time maps out a simple harmonic motion. So here, you can see that even though it's going in a circular path, over time, it's just a wave, right? Where your x can equal a, which is your amplitude. Remember, your amplitudes are how high or how far away the displacement is from the original position. This can just be your amplitude cosine theta to find your x. Theta will be your omega t. Omega will be your 2 pi frequency. And you can also find theta is that it's 2 pi frequency time. Okay? And if you plug in the theta here to the original theta up here for x, you can also find the x in that direction. Okay, so here's a swing with a cute little baby. In order to counteract damping forces, this dad needs to keep pushing the swing. So that damping force is pretty much something that's going to stop you. So eventually, if the baby's just swinging without the dad pushing, it's going to come to a stop. So to counteract that force, he needs to keep pushing roughly around the same force. That way, the baby can keep going back and forth at the same velocity. In this graph, we have displacement versus time for a harmonic oscillator with a small amount of damping. The amplitude slowly decreases, but the period and the frequency nearly stay the same as if the system were completely undamped. So for non-conservative forces, we remember that work non-conserved is equal to the change in total energy, kinetic energy plus potential energy. So here we see that the waves get smaller and smaller and smaller and smaller and smaller, but the period between amplitude here to here, even if you were measuring here to here, it stays the same. So for damped harmonic motion, if you gradually increase the amount of damping in a system, the period and frequency begin to be affected, because damping opposes and hence slows the back and forth motion. The net force is smaller in both directions. If there is a very large damping, the system does not even oscillate. It slowly moves towards equilibrium. And the next figure shows the displacement of a harmonic oscillator for a different amount of damping. When we want to damp out oscillations, such as the suspension of a car, we may want the system to return to equilibrium as quickly as possible. Critical damping is defined as the condition in which the damping of an oscillator results in it returning as quickly as possible to its equilibrium position. The critically damped system may overshoot the equilibrium position, but if it does, it will only do so once. Critical damping is represented by a curve A. We'll get into that, I think, here in a minute. With less than critical damping, the system will return to equilibrium faster, but will overshoot and cross over one or more times. Such a system is underdamped. Its displacement is represented by a curve in the previous figure. So this would be underdamped. Curve B in the next figure represents an overdamped system. As with critical damping, it too may overshoot the equilibrium position, but will reach equilibrium over a longer period of time. So we have A. This is the critical damping. So yeah, it overshoots it, but it evens out, right? For B, this is underdamped, I'm assuming. Yeah, B is overdamped, so it quickly reaches equilibrium and it doesn't even cross it. And for C, we have critically damped oscillators return to equilibrium at x equals 0, and the smallest time possible without overshooting it. So for example, 16.7, so it says damping oscillatory motion is important in many systems, and the ability to control the damping is even more so. This is generally attained using non-conservative forces such as the friction between surfaces and viscosity of objects moving through fluids. The following example considers friction. So suppose a 0.2 kilogram object is connected to a spring, as shown in figure 16.24. But there is a simple friction between the object and the surface, and the coefficient of friction, mu k, is equal to 0.08. So for A, what is the frictional force between the surfaces? B, what total distance does the object travel if it is released at 0.1 meters from equilibrium, starting with the velocity 0? So here they're giving us the constant of a spring is 50.0 newtons per meter. So our solution for A, we are going to choose the proper equation. So friction is going to be mu k mg, right? So real quick, for part A is about frictional force. So this is why we involve friction right off the bat. So for here, we'll have, yeah. So enter the known values. So we know that mu k is 0.08. We know mass is 0.2, and we know g. So our force here is 0.157 newtons. So here the force is small because the system and the coefficients are small. For B, we said that for part B requires an understanding of work and conservation of energy, as well as some understanding of horizontal oscillatory systems. So identify the known for B. The system involves elastic potential energy as the spring compresses and expands, friction that is related to the work done, and the kinetic energy as the body speeds up and slows down. Energy is not conserved as the mass oscillates between or because friction is not a conservative force. The motion is horizontal, so gravitational potential energy does not need to be considered. Because the motion starts from rest, the energy in the system is initially PE, elastic, is equal to 1/2 kx squared. This energy is removed by the work done by friction. Remember, work that is non-conservative is equal to negative FD, where F is the total distance traveled, where D is the total distance traveled, and F is mu k mg, which we found above. When the system stops moving, the friction force will balance the force exerted by the spring. So PE is going to equal to 1/2 kx squared, where x is the final position, and is given by, we have force elastic is going to be our force here that we represented here. Our kx is already dignified as mu k mg. So all we're doing here is trickling it down. So if we're going to find our x, we have to divide by k, right? So that's how you have x is equal to mu k mg. So by equating the work done to the energy removed, solve for distance d. So we have the work done by non-conservative forces equals the initial stored elastic potential energy. Identify the correct equation to use. So for work that is non-conserved, we have this equation that we went over in the previous chapters. But we know that we're going to have our potential energy in the elastic final minus our potential energy elastic initial. So this will give us 1/2 k. Remember, these are potential energies of a spring, so 1/2 k is going to be in each one of them. Where we have for your final, we will have mu k mg over x, which we found just now. And the initial is just going to be your x squared. But we also remember that work that is not conserved is equal to negative FD. So here we enter the friction as F into this equation. So we have negative mu k mgd, where this part here is just your F. Okay? And you just bring the D down. So combine the two equations now, right? Because they equal that work that is not conserved. So we equal them to each other here. And now we have to solve for D. So we just have to isolate D over here. So we just divide by negative mu k mg, which is just down here. The k is still above, and the 2 is at the bottom, right? But we have this negative. So unless we want to put the negative in front, which you totally can, we can just simply switch out these two variables inside, and it is the same as giving the negative throughout the equation. So from here, we're now ready to plug everything in. So you plug in your 50 for your constant, 2 times your mu k, times your mass, times your g. We have our x is going to be 0.1 squared. And again, plug in everything for mu k mg over k and square both. So for d, we're going to have 1.59 meters. Okay, so this is the total distance traveled back and forth across x equals 0, which is the undamped equilibrium position. The number of oscillations above about the equilibrium position will be more than d over x. So that'll be about 15.9 because the amplitude of the oscillation is decreasing with time. At the end of the motion, this system will now return to x equals 0. For this type is of damping force because static friction will exceed the restoring force. This system is underdamped. In contrast, an overdamped system with a simple constant damping force will not cross the equilibrium position x equals 0 a single time. For example, if this system had a damping force 20 times greater, it would only move 0.0484 meters towards the equilibrium position from its original 0.1 meter position. So that follows that graph that we went over here. So for figure 16.25, if you sit in front of a piano sometimes and sing a loud brief note at it with the dampers off, with its strings. It will sing the same note back to you. The strings, having the same frequencies as your voice, are resonating in response to the forces of sound waves that you send from them. Your voice and a piano strings is a good example of the fact that objects, in this case, piano strings, can be forced to oscillate, but oscillate the best at their natural frequency. The natural frequency is the frequency at which a system would oscillate if there were no driving or damping forces. For this figure, we have a paddle ball on its rubber band moves in response to the finger supporting it. If the finger moves with a natural frequency, F naught, of the ball on the rubber band, then a resonance is achieved, and the amplitude of the ball's oscillation increases dramatically. At higher and lower driving frequencies, the energy is transferred to the ball less efficiently and responds with lower amplitude oscillations. So for this figure, amplitude of a harmonic oscillator as a function of frequency of the driving force. The curves represent the same oscillator with the same natural frequency, but with different amounts of damping. Resonance occurs when the driving frequency equals the natural frequency, and the greatest response is for the least amount of damping. The narrowest response is also for the least damping. So here we have heavy damping, medium, and small. So here our frequencies are going to be a lot different between all three mediums. So for here, we have in 1940, the Tacoma Narrow Bridge in Washington State collapsed. Heavy crosswinds drove the bridge into oscillations at its resonant frequency. Damping decreased when the support cables broke loose and started to slip over the towers, allowing increasingly greater amplitudes until the structure fell. So here, you can see these are waves here, if you want to look at it that way. But with these winds crossing back and forth, they were moving the bridge this way, right? So at some point, the force became too strong for these support cables, and that's when they started to break. So once one went, it would strain the rest of the support cables until the bridge actually collapsed. And that will do it for chapter 16. There's, I think, maybe a few more sections that was not covered, but do not worry about those. Again, if you go to the end of the chapter, it'll give you a good summary of all of the equations we go through, and it becomes really handy whenever you are getting ready for your quizzes and your exams.